in in our last meeting, I actually covered basically all the material of Chapter 7 without the examples, and I worked one specific example. Specifically, in Chapter 7, what I did was first introduce a dot product, which is also called a scalar product, but it's a vector calculus type operation. The main point is I'm going to start off from example 7.2 of the textbook. I'm going to try to do probably all of the examples from the chapter, but at least most of them. I've literally, it'd be enough to cover that. And then at the end, I should get enough to get us started on conservation of energy, which is chapter 8. And that's what's going to be on the online test as well as the face-to-face test. So we currently have a face-to-face test and an online test scheduled. The face-to-face test was supposed to be due by like this Sunday for my online classes, but tomorrow at class for my face-to-face classes, and it went up through chapter 8. But in light of me not covering chapter 8 before then, I went ahead, rather than changing the format of the test to just include chapters 1 through 7, I decided to delay it. So now, a week from tomorrow, which I think is March 25th, a week from tomorrow will be the actual day that we're doing the face-to-face test. I think I made the online test due at 11:59 p.m. that day. I really meant to do 11:59 the day before because if you don't take the online test before you take the face-to-face test, you're sort of defeating the purpose of the whole online test scenario. So hopefully you guys will go ahead and take the online test before that. You do get multiple attempts, so you just at least do one of them. That way you'll have it done. And also, there's a high probability that, and I say high probability because roughly somewhere between 20 and 10% of my class often misses an online test. So don't miss that online test because it's going to count as a zero. Or if you realize you missed it and catch up and ask for the chance to take it again, I'm going to take off at least 10, but sometimes I take off 15, 20 points. So anyways, with that being said, let me go ahead and get started. All right, we finally got the iPad open, so I'm going to go ahead and read the first example to you. And as I said, this is like example 7.2 of the textbook, work on a backpack. It says, determine the work a hiker must do on a 15.0 kilogram backpack to carry it up to carry it up a hill of height h equals 10.0 meters as shown in figure 7.4a. Determine also B, the work done by gravity on the backpack, and C, the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity, i.e., the acceleration is zero. Okay, so that actually, I'll tell you what that means and how we're going to implement that and how it's going to be helpful to us as we're solving the problem. But first, I want to go ahead and write down the information that we were given and then draw a diagram. So in case you don't have your book open, you'll still know what we're talking about. So the information we have, for starters, this is example 7.2, and your book calls it 7-2. I usually like writing it with a dot, so I apologize for that, but it's just the way I do it. Uh, the mass is 15.0 kilograms, and that means the weight, which is equal to mg, I believe is 147, but let me double check with my calculator to make sure I'm remembering that correctly. 1.5 times 9.8 gives me 147 newtons. H is the height that we're actually going up to, and that's equal to 10.0 meters. And once you look at the diagram, you'll see that this looks a little weird. So let me go ahead and draw that diagram. What we have is an inclined plane at some angle theta. That inclined plane we're treating as if it's a hill. The person walking with a backpack on is right here. Now, his displacement in this whole process should be him walking from right here to directly above the end of the displacement vector, which should be, of course, right in line with the uh, end of the hill. The other thing that we mentioned, of course, is this height is h equals 10.0 meters. And as I said, this distance vector d is really our displacement, but they don't actually give us the hypotenuse of this inclined plane, so we don't really know what the distance d is, so it might look a little confusing, but that's the diagram. Now I just want to go with part A. They are wanting specifically, I don't know why I changed my color to purple by accident when I was doing the text, but anyways, A, they want to know the work the hiker must do. So I'm going to say W sub H for hiker is equal to question mark. B, they want to know the work done by gravity. So I'm going to call that W sub G. And C, they want to know the network, which is just the summation of all the works done on the backpack. Okay, so that means with all the forces. Now, from according to the description, the only forces acting on it are uh, the gravitational pull from the Earth, so that's pulling it down. And then, of course, the backpacker is putting a force in the upward direction to hold the backpack up. But moving at constant speed means that he can just completely, he or she, the hiker, can completely move left and right all they want. And since it's at constant acceleration, the total force in the x direction is zero. So we really only have the y direction force downward and the y direction force upward. Upward being the force of the hiker, and downward being mg, the 147 newtons. And we're also imagining it going at constant acceleration, so the acceleration in the y direction is also supposed to be equal to zero. So we can convert this in a second to a free body diagram as follows. So here's the backpack. It has a mass m. Acting on it, of course, is a weight W equals 147 newtons. And then acting the other direction, and technically these should be the same length, but I'm not really trying to draw it to scale. This is the force due to the hiker, F sub H. Now I should also say that the vector D I could put on here as well. Notice I'm putting that in just for some organization of what directions things are in. That's not technically a force, so it's not really normally part of the force diagram. I'm just trying to draw it so you'd understand what we're doing with that. So in that mind, I'm just going to draw this off as a dash. But the main thing is we can see that if I compare the angle of that D vector to the x-axis, that's the angle theta that we're talking about. That's partly why I did it. And then that also means we could complete this with a right triangle, and this angle would be 90 minus theta, and we'll call that angle phi. Now, if you notice this vertical line right here I drew in dashes, that line is vertical, as is the green vector is vertical, and because of that, this angle right here is interior to the two parallel vectors, and in this case, it's below the transverse line. So there's a line going across these two parallel lines. This parallel line has a traversing line going this way. This is one of the interior angles, and on the alternate side of the interior angles is this angle. And by our knowledge of geometry, we know that alternate interior angles are equal when the two lines that the transverse crosses are parallel. So that tells us that this angle down here is also phi. So that's the 90 minus angle. Uh, in addition, you really need to know what this angle right here is, which I'm going to call alpha. Actually, I don't like my alpha. I'm going to call that gamma. So there's our another Greek letter we can use. But the main thing is we're trying to calculate this work, and I'm going to need this diagram. So we can start off with our solution. And our solution is going to involve the summation of forces is equal to mass times acceleration. It's going to involve the idea that work is equal to the integral of F dot dl. And we're also making use of, though we already made use of it, weight is equal to mg, which equals 147 newtons. So that's the stuff we're making use of. For part A, we're going to calculate the work done by the hiker. And the work done by the hiker, since notice it doesn't, there's no need for this force to vary in time. It's going to be essentially the same force, and it's going to be acting on the backpack by the hiker the whole time. The angle that it makes, that force makes with the displacement vector d, doesn't change either. So we're not required to actually do the integral part. We just need to do the dot product part. So it's going to be basically FH dotted with the D vector. And now you can start to see, because the work required us to do F hiker dotted with the D, you can see why I included the D vector on there on the free body diagram, even though it's not technically a force, so it shouldn't be part of the free body diagram. Hopefully that makes sense to you guys. Now, with this in mind, we have to use the summation of forces in the y direction to figure out what F sub h is. So I will do that down here. The summation of the forces in the y direction equals mass times acceleration in the y direction. As I already argued, the acceleration in the y direction is going to be assumed to be zero, and the forces actually acting are F sub h plus the negative of mg, because the direction of the weight vector is downward. So I would normally remind everybody that the left-hand side of Newton's second law, the summation of forces, is a sum of forces, not a subtraction of forces. But when they're oppositely directed, one has to be positive and the other one has to be considered negative. So that's why I'm writing this as if it's FH minus. It's really FH plus the negative mg. But in this case, I'm going to say FH minus 147 newtons is equal to 0. And obviously that gives us that FH is equal to 147 newtons. So remember, in order for someone to actually lift a backpack, they have to apply a force to it that completely cancels out the force of gravity, which is what this FH did, because its FH is 147 and W is pointing downward and is also 147 newtons. So that's just barely enough to keep it from being accelerated downward. In order for it to actually move upward, you'd have to put just an infinitesimal amount of force more. We're going to pretend like that part of the force is not really acting, because that would actually cause an acceleration. So in principle, we actually technically have to give it a little bit more force than the 147 newtons, but we're not too concerned about that, because we're going to sum it up and work it out that way. So here we go. The force in the horizontal direction, or excuse me, the force of the hiker is 147 newtons. And remember, the dot product is also given by A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them when they're tail to tail. So this is the magnitude of the first vector. The magnitude of the second vector we don't know yet. I'm just going to call it D. We can work it out. But I still need to find the angle between the D vector and the F sub H vector. So I write down cosine, but I need the angle phi, because the angle phi is the angle between FH and D when they're tail to tail. So we already figured out that the angle phi was equal to 90 minus theta. So I'm going to say cosine of 90 degrees minus, oh, excuse me, minus theta. I wrote phi again. So that's what we're working out. There is a trig identity that I'm using here, and let me go ahead and just write both of these things down. What I just used was A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. The other thing I'm going to use is cosine of A plus or minus B is equal to cosine A. Ooh, I wrote cas A. Didn't mean to do that. One more at the back. Okay. Cosine A cosine B minus plus sine A sine B. So that's actually the identity we're going to use. In this case, we have cosine of 90 minus theta. So cosine of 90 minus theta has got to equal cosine of 90 degrees times cosine of theta. Now we use the bottom sign minus, so that means we got to use the bottom sign over here, so that's the plus. And then I'm going to write the sine of 90 degrees, which we all know is 1, times the sine of theta, like that. So now what we can see is we have, because cosine of 90 is equal to 0, we can see that the cosine of phi, which is 90 minus theta, that cosine of phi is just equal to sine phi, which is the whole reason why we call the sine function sine and then we call the cosine function cosine, because the sine of an angle is the complement, i.e., CO, the complement of the complementary, or I should say, it's the uh, angle of the complementary angle. So, for instance, when you take the sine of an angle theta, cosine of 90 minus theta should give you the same thing. That's really it. And but that's why they called it sine and cosine, because one gives you the sine of the complementary angle. So, for instance, if you said I know sine theta, then you can take the cosine of it, and you will get basically the cosine of 90 minus 90, which in this case would be cosine of 0. So, anyways, hopefully y'all are understanding what I'm saying there. Uh, if not, don't worry about it. It'll come to you later. But now that I've done this, I can now say this is going to be 147. Now, I'm going to make use of the trig that I can see here. And from the trig of this diagram, I can see that uh, cosine theta is equal to adjacent over hypotenuse. So that would be d sub x over d. I don't know d sub x either, so that's not very helpful. But then I can also try sine of theta. That's equal to opposite over hypotenuse, which is h over d. So that allows us to figure out that d is h over sine theta. So I'm going to write this as h. Oops. Write it back in yellow. I'm going to write this as h over sine of theta. And then, of course, we just worked out that cosine of 90 minus theta is the same thing as sine of theta. So now we can see that the sines cancel one another out. And because they cancel one another out, all we have to plug in there is just the h, because we don't know the angle theta anyways. So 147 newtons is what we have, and I should have put that in there too, times h, which is 10.0 newtons, gives us 1,470 joules. Remember, a newton times a meter is a joule, and I underscored that last digit because that is not a sig fig. So what I'm going to say is the work done by the backpacker is equal to, and this is the way you're supposed to write it to make sure you don't use non-significant digits. You're supposed to write this as 1.47 times 10 to the third joules, and that works fine. And if I use this calculation in subsequent, if I use this number in subsequent calculations, I'll end up using 1.470 because that is the other digit. And you always want to carry at least one other digit. So there's our work done by the hiker. Now we can do the work done by the gravity. So for part B, work done by gravity is basically the force mg, which is 147 newtons, times the distance. Remember, we're just using a dot product here, so it's magnitude of the first force, which is the weight, times the magnitude of the second vector, which is the displacement. So we're going to put d there. And now we need to know the angle between the two. And you can see the angle between W and D when they're tail to tail is the angle gamma that I showed you. So we're going to write this as cosine gamma. Okay. Now we also know that D is equal to the uh, H over cosine or H over sine theta. So I can make that adjustment 147 newtons times H over sine theta times cosine gamma. Now, cosine gamma, we can see, is specifically the cosine of 90 plus theta. So doing that, cosine of 90 degrees plus theta is actually equal to cosine 90 degrees, which of course is 0, times the cosine of theta. And this time we're using plus, so it's the top symbol, and that means we stick a minus in here, and then it's the sine of 90 degrees and times the sine of theta. Now, in this case, the sine of 90 we know is 1, and we now get a negative sine of theta for the cosine of 90 minus theta. So that's going to be times negative sine theta. Luckily, the trigonometry gods allowed those trig functions to cancel out, and we now have that the weight due to, or the work done by gravity, I changed my pen to the wrong color. The work done by gravity is now 147 newtons times -1 for the negative in front of the sign times 10.0 meters for the H, and therefore we get 1.470 times 10 to the third joules negative. So the work done by gravity is negative 1.47 times 10 to the third joules. Circle that. We now have the answer to part B. And of course, the answer to part C, which was supposed to be written in blue, so let me do that again. The answer to part C was W net, which equals W hiker plus W gravity, which equals 1,470 joules plus negative 1,470 joules equals 0.000 joules. So the net work done is equal to 0 joules. And luckily, my class, we started talking about the work energy theorem on the very first day. So I've already told you that the total work done, according to the work energy theorem, on any object, the total work done is equal to the change in kinetic energy. As we express in this problem, you're supposed to imagine the hiker walking in a smooth motion at constant velocity. And since the velocity is constant, that means 1 half mv squared, where v is the velocity, is also a constant. Therefore, the kinetic energy change is 0, and therefore we expect the network to be 0, and that's what we just found out. So by doing it that way, we were able to make this example 7.2 not only an example of computing a dot product and calculating work, but specifically we're actually now made it into a application of the work energy theorem as well. So that's it. Normally, of course, this is where I would ask if anybody had any questions, but there's no one here today, so I'm going to keep on pressing forward. And you can check your work on this one, or you can check the example on this one, and you'll see that my work gave the same answers as the textbook did. The next example is actually a conceptual example, 7.3. It says, does the Earth do work on the moon? The moon revolves around the Earth in a nearly circular orbit with approximately constant tangential speed, kept there by gravitational force exerted by the Earth. Does gravity do A, positive work, B, negative work, or C, no work at all on the moon? Well, if you look at the diagram that they give you, figure 7.5 in the book, what you basically see is there's Earth, And then we're pretending, even though it's technically elliptical, we're pretending the orbit's a perfect circle. In the context of pretending the orbit is a perfect circle, then we know v squared over r is the necessary acceleration that has to happen for it to maintain that circle. And that v squared over r is supplied by a force of gravity, so that the force of gravity has to be equal to m, the mass of the moon, times v squared, the velocity, tangential velocity of the moon, divided by r, the radius of the orbit, which goes from the center of the Earth to the center of the moon. The main thing, though, is to see that the gravitational force points this way and the tangential velocity points this way. And remember, displacement is just the velocity times time when you're going at a constant speed. So if you consider the displacement in a very small time interval, what you'll see is the displacement is exactly perpendicular to the force of gravity, and therefore the work should be zero. Okay. If you think about the fact that it's actually elliptical orbit, then you'll realize there's a point at which the Earth is here and the moon's at its absolute farthest away, and that's called aphelion. Sorry, I keep wanting to use the word geo instead of the word uh, dang it, I just lost it again. Crap. So it's not geocentric, but heliocentric. Excuse me. In this case, it is geocentric. So this is apogee and perigee. That's the part I was going for. So apogee is when it's farthest from the moon, and then perigee is when it's nearest. I said that wrong. Apogee is when the moon is farthest from the Earth, and perigee is when the moon is nearest to the Earth. So when what we learned from Kepler's laws of motion is that when it's actually farthest away, in other words, at apogee, then the moon is going its slowest. That means for that whole half of an orbit, it actually is speeding up, 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 and then it gets at perigee, at which point it's reached its maximum velocity, and then it starts to slow down, 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 until it gets back to apogee where it's at its lowest speed. So in both parts of that, there must, since it was speeding up in the elliptical orbit, there must have been a component of force that was somewhat parallel to the velocity, or was specifically parallel to the velocity, and a component that was perpendicular to the velocity. So in elliptical orbit, the gravitational force can actually do some work, and then it does more or less the negative of that amount of work on the second half of the actual orbit. So the first half, it's doing some positive work until it reaches perigee, and then from there on out, it's doing negative work because it's actually slowing it down. So that's the difference between reality, which is that it's a slightly elliptical orbit, and the assumption, which was that it was a perfectly circular orbit. So when it is a perfectly circular orbit, the gravitational force does no work because the force and the displacement are perpendicular to one another. But when it's an elliptical orbit, the force and displacement have a parallel component. So because of that parallel component, it can do work. Again, this is where I would ask if anybody has any questions, but we don't have anybody attending right now, so I'm just going on. Uh, at this point in your book goes about talking about the dot product, which we've already covered as well. So I'm just going to jump into example 7.4. Example 7.4 tells us the force shown in figure 7.7 has a magnitude Fp equals 20 newtons and makes an angle theta equals 30 degrees to the ground. Calculate the work done by using equation 7.4 when the wagon is dragged 100 meters from the ground, along the ground. So basically what they're telling us, and I'll draw a diagram, but what they're telling us is that we have a force Fp whose magnitude is one, no, is 20 newtons. And I'm going to call that 20.0 just so we can have three sig figs. And that pulling force Fp is at an angle theta equals 30.0 degrees. Again, I added an extra sig fig. Uh, Now, in order to make sense of all this, we need a diagram of some sort. So what we're looking at is, in fact, a force of 20 newtons at 30.0 degrees. I really made that a lot smaller than it needed to be, and I don't think I should have done that. So let me extend this vector just a little bit more so I can get a little bit more angle here. So this angle is 30.0 degrees, and that means that this force has a positive y component, and it also has what we would call, and actually I normally call positive a green or something like that. So it has a positive y component, and if we consider the x-axis as being positive pointing to the right, then it also has a positive y component. And we can figure out what those are by realizing that this 20 newtons is the magnitude of the hypotenuse of this right triangle, and then we can use sine theta is equal to opposite over hypotenuse. That would be FP sub y over 20.0 newtons, and cosine theta would equal FP sub x, and that's over 20.0 newtons, and that gets us what we need. Now, when we go to compute that, we can tell, for instance, that the x component is going to be 17.32 newtons, and the y component is going to be 10 newtons. So from that alone, we can now build the vector, and the vector FP is equal to 17.32 newtons in the I hat direction plus 10.0 newtons in the J hat direction. And we can go further and say that the displacement vector D is equal to 100.0 meters, and that is in the I hat direction. So, if I continue far as drawing this diagram goes, what we would see is there's a mass M, and there's a force FP acting, and that force and this displacement vector, which I will draw in green, that force and this displacement vector actually, when tail to tail, are separated by the angle theta, which equals 30.0 degrees. What we're using for this solution is obviously we've used trigonometry, but that's just par for the course. But we're also going to use work is equal to the integral of F dot dl. But again, in this case, it's just a constant force. The force not only is constant, but the direction is constant, and it doesn't change with respect to the d vector anywhere along it. So this just reduces to work is equal to F dot d. Because of that, we can go ahead and calculate the work. So the work is equal to F dot D. F is in fact going to be 17.32 newtons I hat plus 10.0 newtons J hat dotted with 100.0 meters I hat. And when you do this dot product, you get 17.32. I should have underlined that. Oop, no. That one I should not have underlined, but the two I should have. 17.32 newtons times 100.0 meters plus 10.0 newtons times 0.00 meters. That's for the J component or the J hat or Y component of the displacement vector, for which there is none. So we get basically 1.732 times 10 to the, now we can see that's 10 to the third, because 100 times that would be 1,732. So this would be 1,732. Yep. And Newton times a meter is a joule. So that's the actual work done. Anybody have any questions on that? Is what I'd normally ask again, but I can't because nobody's here. All right. So that's the answer to example 7.4. I'll circle it off. And now we have some understanding of how we use the dot product as well. Even though I've already shown you a dot product, at least now you've seen a dot product with actual applications to a specific physics problem. So, it's just another line of inquiry so we can look at the dot product and learn something about it. So now you've seen it with pure numbers as well as numbers with units. You can see, if, for instance, that the I hat truly is a unit vector, meaning its magnitude is 1 unit, not 1 meter, not 1 Newton, not 1 joule. It's just 1 unit. And the same thing with the J hat vector and the K hat vector. In fact, in my class, it's the same with all the hat vectors. If I make a hat vector, that's supposed to be a unit vector. All right, now we're going to go on in section 7.3. They talk about the work done by a varying force. And of course, I want to reiterate something that you're supposed to have learned from calculus. And it's probably the single most important, but single simplest facts that you recall from calculus. So, for instance, I would like to ask you. Obviously, you're not here, but I'm going to ask you anyway. So I want you guys to think about it. Maybe pause the video, think about your answer before answering it, and then answering it. But what did we learn that calculus can give us about a specific graph? Like if, or let's say it this way. Uh, what did we learn about the derivative with regards to the graph of the function you're taking the derivative of? So again, let me restate that. What did you learn the significance of the derivative of a function is relative to the graph of that function? Alternatively, there's another question that's important as well, and that is, in considering the integral of a function, what does that integral give you with regards to the graph of that function? Okay, so those are two fundamental concepts that you learn in calculus, that the derivative gives you something related to the graph of the function that you took the derivative of, and that the integral gives you something related to the graph of the function that you're integrating, and I'm asking you what that is. Now, again, you should have the video paused long enough because I'm getting ready to tell you the answer, but you should come up with this answer on your own. So now I'm going to say that the answer to the question is the derivative of a function is, graphically speaking, the slope of that function. So if you take the derivative at a specific point, it's the slope at that point. If you get a derivative that's a constant, that's the slope everywhere. Okay. Alternatively, the integral of a function relative to its graph gives you the curve, gives you the area under the curve. So that's something that you just got to remember, because there will be questions where I'll just have a graph of a function as a function of position, and you could, in principle, be asked how much work is done from x equals 3 meters to x equals 4.2 meters. And that means, oh, I've got to figure out the area under the curve between x equals 3 meters and x equals 5.2 meters, or whatever numbers I said. All right, so keep that in mind. Now we're going to remind you that work equals integral of f dot dl does tell us that work is the actual area under the curve. If you actually did a closed path, then it would be the area inside of that closed path. And of course, if that was a conservative force, the network done in a closed circuit is zero, which we'll learn later. But in this case, it's not. So now that we have stated that, what we can do is first examine the work done by stretching a spring. So, and this is more or less like a derivation, not a problem. So I just want to line it off and give it to you as a derivation. So what we're doing here is we're picturing a wall with a spring attached to it, like this. And you can imagine a mass being on it, or you can imagine just a little block that's like a handle or something. You can imagine that. And what we're going to do with this is we're going to imagine that this position right here is the vertical line there is the y-axis, and the horizontal line here is the x-axis, so that when the spring is actually at equilibrium, the right-hand side of that little handle is actually at the origin. If I then go around and try to stretch it, what's going to happen? is it's going to stretch. So what we have here is that it moved out a distance x. That's in stretching the spring. If we compressed it, it would move a distance to negative in the negative direction. But the main thing is now we're going to calculate that work done. Work is equal to the integral of F dot dl. Now, what we're going to introduce is something called Hooke's law. Hooke's law says that when you apply a force to a body that either compresses or tends to stretch the body, then the force that that body applies back to you is equal to the negative of some constant times the amount of stretch or compression you did. So, and notice the negative sign is just indicating the direction. So, for instance, if I pulled the handle in the positive x direction, that would mean x is a positive quantity, and k times x, since k is a constant and it happens to be positive, that means k times x will be positive. And then the negative in front of it tells you, oh, I'm pulling it in the positive x direction, and the force, the restorative force of Hooke's law, is pulling it back in the negative direction. In other words, it's trying to fight any change. So additionally, like if I decided to push it into the left, then my x is negative, and if I multiply the negative x times a positive k, I get a negative number. And then if I multiply that by -1, as the sign in the equation says, then I get a force in the positive direction. And that's true too, because the restorative force, or the nature of a restorative force, is that when I compress it, that's me pushing it in the negative x direction, it's going to try to get back to its original state by pushing in the positive x direction. And that's what happened when you have it a negative x in F equals negative kx. You get positive kx. So that's Hooke's law, and it applies to all bodies, but in order for us to see it in the lab situation in a safe manner, we don't want to try to compress or stretch, actual pieces of metal or 2x4s or anything like that, because the forces required to make measurable changes in their length are so large that people could really get hurt. So we basically just use a spring because that shows the behavior exactly with a lot less force. That being said, both in the case of it being a real, iron rod or a 2x4 or whatever, there is a point at which you can stretch it too far that it no longer obeys the Hooke's law. The restorative force F is equal to negative k times x, and that's true with a spring as well. If you've ever seen a slinky, when you first buy them, they just look like a bunch of rolls or a bunch of circles stacked on top of each other. But if you've accidentally pulled that a little too hard, what you'll find is one of those little rings in the spring will get bent, and then it no longer sits flat. That's the part that's saying, hey, at least on this link that's sort of jacked up, and maybe the length on either side, or a couple of loops on either side of that particular crimp, if you will, those are not going to obey F equals negative kx. Okay. So within the elastic parameters of the material, then F is equal to negative K times X. But if you exceed the elastic parameters, then it's not going to behave that way. In fact, if you pull too hard, for instance, on a metal rod, it will do what they call neck down. So you have, let's say a rod that's 1 inch in diameter, and you're pulling on it so hard. If you pull it so hard that it's no longer responds linearly, like according to Hooke's law, then what'll happen is the diameter, at least in that one part, is going to shrink down, and it'll stretch, and it'll move quite easily. In fact, once you've reached that breakdown strength, it actually becomes a lot less strong, at least while you're in that mode of stretching it or compressing it. So, necking down is what happens when you stretch it. Of course, if you compress it, it tends to squish up or maybe even bend or break. So. All right, with that in mind, we can now put in the force. Again, we're wanting to calculate the work done by the person, so we're not going to use F equals negative kx because that's the force by the spring. So in this case, when we stretch it to the right, that meant the force was actually equal to k times x, because that's what it has to be big enough to do to stretch it in amount x. So at 1 centimeter, it's k times 1 centimeter. At 2 centimeters, it's k times 2 centimeters, so on and so forth. And of course, this is pointing in the positive x direction, so I'll put an I hat by it, and then I'll do a dot. And the DL is a differential path element. Uh, and normally we take it as like a little tangent vector or whatever, but the main thing is it's a differential of a line segment. In this case, I've aligned the setup so that the alignment of the displacement is directly along the x-axis. So I'm going to call that differential length just dx, and it's going to point in the I hat direction. So I'm going to call dl dx I hat. Remember, this is technically a path integral or a line integral, and that means when you're doing that, you either need to indicate the direction by the direction of the DL and have the limits of integration just in the positive coordinate direction, or you need to use the limits of integration to indicate which direction you're integrating, and then you just point DL in the positive coordinate direction. In this case, we're both going in the positive direction, so it's virtually no way you could get it wrong. So we're just going to do that. Now, again, the dot product is what we call a linear operator. That means I can pull all that non-vector stuff out to the side and just let the vector operation, which is a dot product, act on just the vectors. So that gives me k times x times dx times I hat dot I hat, and I hat dot I hat is 1 because remember, a dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. A unit vector has a magnitude of 1 unit. So in this case, I hat dot I hat is 1 times the cosine of the angle between I hat, which is obviously 0. So 1 times the cosine of 0 is just 1. That's why we get that. And in this case, we're going to get 1/2 kx squared from the integral, and that's to be evaluated from x equals 0 to just plain x. Therefore, the work done in compressing or in stretching a spring is 1/2 kx squared if we stretch it a distance x. Now, if I did the same thing for compression, what you'd see is the following: work compression is equal to f, the integral of f dot dl. So in this case, I'm going to take the integral, and in this case, I'm actually pushing in the negative direction, so it's going to be negative k times x times I hat. That's my F compression. And then the stretch is actually going to be in the negative x direction. So this is where I have to choose either letting the DL indicate the direction or let the limits of integration represent the direction. I'm going to choose to let the DL represent the direction. So I'm going to say this is negative dx I hat. Now, doing that, that means the limits of integration have to go in the positive coordinate direction. So I'm going to integrate as if it's going from 0 to, or actually, I should integrate as if it's going from uh, negative x to 0. So actually, I should probably put that the other way. So it's going to go from negative x to 0 because really what I'm doing is I'm compressing it from 0 to negative x, where x is the amount of stretch or compression that we're using, and that is a innately positive quantity. Now, with this, we can see that the two negatives give us a positive, so I end up getting positive integral negative x to 0 of kx dx times I hat dot I hat, which again we know is 1, and of course this gives 1/2 k x squared evaluated from negative x to 0, and lo and behold, we're just going to get 1/2 k x squared again. So it turns out that formula 1/2 kx squared is the work done in compressing or stretching a spring by a distance x. And the k constant, by the way, is called a spring constant or a spring stiffness constant. So Hooke's law is something that we use over and over and over again, and it's not because we're that interested in springs. It just turns out that things that operate linearly, which f equals kx, is just like y equals mx plus b, except the plus b part is 0. So that linearity is something that is mimicked all over nature. For instance, if you're just talking about what the force is that is holding one atom near another atom, when you're near its equilibrium point, the force really goes like some constant times x, which you can see from a Taylor series expansion. We'll talk more about that when we get to that part, but I just wanted you to know that that is what we're doing here. So now I've got this new formula, W equals 1 half kx squared, and I want to solve another physics problem. So I'm going to go to example 7.5. And example 7.5 is called work done on a spring. A person pulls a spring in figure 7.10, stretching it 3 centimeters, which they say is equal to X max, which requires a maximum force of 75 newtons. How much work does the person do? And then B, if instead the person compresses a spring 3 centimeters, how much work does the person do? So they're saying in the first case, how much work is done in stretching the spring 3 centimeters. And then in the second part, they're saying how much work is required to compress the spring 3 centimeters. And they've given us that it took 75 newtons to to stretch the spring 75, or excuse me, 3 centimeters. So that should be enough information for us to determine what K is. So what I have here is x0 is just zero point 0.0 meters. I have x max is equal to 3.0 centimeters, which is 0.030 meters, and F max, the force that's applied when I got that stretching of 3 centimeters, is actually equal to 75 newtons. So for part A, the work done is, and we're using this by the way, solution work equals 1 half kx squared in stretching or compressing a spring a distance x. So work is going to be 1 half k times x squared, but we don't know k yet. However, what we do know is F equals kx by Hooke's law. This is Hooke's law for the magnitude. I'm just leaving off the negative here. Uh, Hooke's law gives us that 75 newtons is equal to K times 0.030 meters, and that tells us that K is actually equal to 75 newtons divided by 0.030 meters. And of course, that means we're multiplying 75 by 100. That gives us 7,500, and then we're dividing it by 3. So that gives us K is equal to 2,500 newtons per meter. And just to make sure I didn't make a careless mistake, I'm going to throw that in the calculator to double check I didn't make a boo-boo. Uh, and yes, that's 2,500 newtons per meter. So now we can say work done in stretching the spring is 1 half times 2,500. And actually, both of those zeros should be underscored because neither one of them was a sig fig. We only had two sig figs. So that's newtons per meter times 0.030 meters. That's going to be squared. Notice the meter squared times newtons per meter cancels out the meter in the bottom, so I just get a newton meter, and a newton meter, of course, is a joule. So now I can go ahead and calculate this. Zero point 0.5 times 2,500 times 0.03 squared gives me 1.125 joules, and we only had two sig figs, so technically these two are not significant, but that's the work done in stretching. So now I'm going to do part B, and part B is the same thing, only now we're doing it under compression, and as I showed in the last calculation, work done by compression is the same formula, which equals 1 half times 2,500 newtons per meter times negative 0.030 meters. And of course, since it's squared, that means the negative is going to disappear. And this is really the part where we're showing you again that it gives you the exact same value. So this is 1.125 joules equals W compression. So that's example 7.5. Again, this is where I'd normally ask if anybody had any questions. Uh, and you can look at the solution in your textbook and you'll see it's exactly the same as we got here. Now I'm going to do another example. And in this case, it's example 7.6. And example 7.6 says force as a function of x. A robot arm that controls the position of a video camera, see figure 7.12, is in an automated surveillance system is manipulated by a motor that exerts a force on the arm. Assuming that the force is given by F sub x equals F0 times parenthesis 1 plus 1 over 6 x over x0 quantity squared, close parentheses, where F0 is equal to 2.0 newtons and X0 is equal to 0.07 meters, and x is the position of the end of the arm. If the arm moves from x1 equals 0.010 meters to x2 equals 0.050 meters, how much work did the motor do? So that's a really big mouthful. The main thing is we've got a robot arm. They've given us a function that's only a function of x, and obviously we must be moving this camera or whatever in the x direction, so that we're basically just doing a dx or a dl is equal to dx I hat, and the fx is the force is actually this force magnitude times I hat. So let me write down what the force is. The force as a function of x is equal to F0 times 1 plus 1 over 6. And the way I like to say it, even though it's not that convenient to compute it, the way I like to write it so that it makes more sense is I like to write it as x over x0 quantity squared. And if that's the case, then I should make this into a square bracket instead of a round bracket. Now, or parenthesis. So now I'm going to say that the force F is equal to F0 times 1 plus 1 over 6 times x over x0 squared I hat. So that's the force. They also gave us the information that F0 is actually equal to 2.0 newtons, and X0, the quantity that's in the function, is actually equal to 0.0070 meters. And we're wanting to move the bar from X1 equals 0.010 meters to x2 equals 0.0. Oh, that was, I need another zero. Oh, I did put there, 0.50 meters. I thought I left the zero off between the one and the M, but I had not. I just wrote it so close to the M that I didn't notice it. So, so that's what we're supposed to calculate, is what is the work done in moving that way. So in this case, I'm going to say work is equal to the integral of f dot dl. In this case, we're going to get the integral of f0 times 1 plus 1 over 6x0 squared. Notice how when I go to do the integral, it's much more convenient to have the x and the x0 separated. That's why I wrote it this way. Times x squared times I hat, and then all of that is being dotted with dx I hat. And I'm going to go from x1 to x2 as my limits of integration. Notice everything I'm doing is evidently going in the positive direction, so there's no ambiguity in just writing everything out like it's an integral. That's the nature of this line integral. Is if you're doing everything in the positive coordinate direction, it's almost impossible to screw up a line integral. So the important thing, though, is you don't always have to do the thing in the positive coordinate direction. And if you did that, you might occasionally get a wrong sign if you don't understand what's going on. So that's why I'm trying to teach it to you. All right, so now I can go ahead and say, let's use the principle of the linearity of the dot product. So I'm going to take the integral. For starters, I'm just going to pull the f0 out in front because clearly that is a constant. So f0 is going to be pulled out in front. And now what I have is 1 plus 1 over 6x0 squared times x squared times dx times I hat dot I hat, which again is 1. And again, this is integrating from x1 to x2. And this gives me the integral. Let's say f0 is going to be out here. There's my curly bracket. The integral of uh, x, or excuse me, the integral of dx from x1 to x2 plus 1 over 6x0 squared times the integral of x squared dx, like that. And then that gives us f0 times x. Now I'm going ahead and realizing the integral of dx is x, and then evaluated from x1 to x2 means I'm going to get x2 minus x1 after I evaluate that integral at its limits of integration. Plus, or range of integration, plus the other case, I'm integrating x squared. Integral of x squared is 1/3 x cubed, so that's going to become not 1 over 6, but 1 over 18. So 1 over 18 x0 squared times the integral of x squared, like I said, was 1/3 x cubed. So now I have an x cubed. I've already put the 3 down there. And of course, I'm evaluating the x cubed at the limits of integration. So this is going to be times x2 cubed minus x1 cubed. Notice the x's cubed canceling with the x's squared gives us just x in the numerator, which is good because I have to add this quantity to x2 minus x1, and those are all also having just units of meters. So if it wasn't for the x0 squared in the bottom, I'd have the wrong unit. So you can see that was sort of the purpose of it. Now, we can go ahead and plug these numbers in. That's 2.0 newtons times parentheses. In this case, it's 0.050 meters minus 0.010 meters plus 1 over 18 times 0.0070 meters squared, like that, times, now we're going to have 0.050 meters cubed minus 0.010 meters cubed, like that. And I just basically promoted the square bracket to a curly bracket. So that's what happened there. All right. So now I can go ahead and compute what this works out to be. 0.05 minus 0.01 is obviously 0.04, and then when I multiply that by 2, you get 0.08. So I've got 0.080 joules. Now I also have plus 1 over this 18 stuff, so I'm going to say 1 divided by 18 times 0.007 squared in parentheses. This gives me 1,134. Obviously, that's a lot more sig figs than I really have, so I got to underline the non-significant figures. And this is meters to the negative 2 power times now 0.05 cubed minus 0.05 cubed minus 0.01 cubed gives me 0.000124. And then if I multiply that by the 1133.7868, I'm carrying a lot of extra digits in other words. When I multiply those two, I get 0.080 joules plus 0.1406 joules. Oh, by the way, this one was just meters cubed. So in this case, I get, ooh, I still haven't multiplied by the two. That's what it is. So I've got the 14.06 times the point zero 0.02 or the 2.0. Oops, I see what I did right here. I never pulled the 2.0 newtons in there. So this still needs the 2.0 newtons in there. So glad I caught that. So now I'm going to multiply that by 2, and I get 0.28 plus 0.08 is equal to 0.3612 joules, and obviously there's two extra digits that aren't sig figs there, so I'll underscore them. So the work is actually equal to 0.36 joules. If I needed to use that in a subsequent calculation, of course, I would at least carry the 361, but I probably would carry the 3612 as well. Again, this is where I'd ask you for questions, but I have nobody in attendance, so I'm just going to press on. That was example 7.6, and that was the same answer the book got. It got 0.36, but the book did mention to you, showing you the actual graph, which you could use Desmos or just make your own or whatever, and then you could compute the area under the curve, and lo and behold, you'd find it's 0.36 as well. So keep that in mind. The area under a force versus distance curve can be treated as the work done. So that's another physical interpretation that we need to understand. So I've now done example 7.6, and I think I only have like a couple more types of examples that I'd like to work because I just need maybe another work energy theorem example. So I'm going to start with example 7.7. And example 7.7 says kinetic energy and work done on a baseball. A 145 gram baseball is thrown so that it acquires a speed of 25 meters per second. What is its kinetic energy? And B, what was the net work done on the ball to make it reach its this speed if it started from rest? So again, a 145 kilogram baseball is thrown so that it acquires a speed of 25 meters per second. A, what is its kinetic energy? And B, what was the network done on the ball to make it reach the speed if it started from rest? So that's what we're doing. What we're going to write down here, of course, is M is equal to, and I'm going to go ahead and put that in kilograms. So it's 1.145 kilograms, and the velocity is v final is equal to 25 meters per second, and it started from rest, so I'm going to say v initial or v0 is zero point 0.0 meters per second. And what they're wanting to do is in part A, they're asking you for k equals question mark. In part B, they're asking you for the work done. So that's what we're going to do. Solution requires the definition of kinetic energy, which is 1/2 mv squared, and we need the work energy theorem, which says W net is equal to the change in kinetic energy, and of course the change in kinetic energy means K final minus K initial, like that. That can also be written, of course, as 1/2 m times v final squared minus v0 squared, like that. So let us begin. We first want to calculate the kinetic energy. So part A, K is equal to 1/2 times 0.145 kilograms times 25 meters per second squared 25 times 25, I think is 625 times 0.145 times zero point 0.5. So zero point 0.5 times. So now I've got 1/2 times 0.145 times 25 squared, and that gives me 45.31 joules. And if you look, it's a kilogram meter squared per second squared. A kilogram meter per second squared is a newton. So a kilogram meter squared per second squared is a newton meter. And of course, a newton meter is a joule. So this is K final, which is what they were asking for. I've got that answer. Now, the other part they wanted to know is what was the net work done? Well, the net work done, and actually, I should have written this as net because they explicitly told me or asked us for the network. So I should have written net down here. I'm going to write it now and hopefully a little neater than I just did. So the work done, I just tried, I literally just pushed to make that a black, but black letters, but somehow it made it red anyway. So I'll just keep on going. Now I've got it in black for sure. So according to the work energy theorem, W net is equal to K final minus K initial. But we've learned that K initial is zero because V initial is zero. So the work net is actually equal to 45 joules. Again, if we needed that for a subsequent calculation, we'd use 45.31, but that's sufficient. Now there's a nice example to estimate, and that's example 7.8. So I'm going to press on. Example 7.8. Okay. Example 7.8 says work on a car to increase its kinetic energy. How much work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Very straightforward question. So we say W equals question mark, and that's again W net equals question mark. I don't know why I keep leaving that off. Let me just write it. So W net is the question mark. The mass is 1,000 kilograms. The initial, I'm using an I this time instead of an O. Don't know why I just did. We're going from 20 meters per second, which I'm treating as if it's two sig figs, to V final, which I'm also treating as two sig figs, like that. And what they're asking is, again, how much work is needed to accelerate it. So what we know is solution W net is equal to K final minus K initial, and we're using the fact that K is defined to be 1/2 mv squared. So now I can calculate W net is equal to 1/2 mv final squared minus V initial squared, which equals 1/2 times 1000.0 kilograms times 30.0 meters per second squared minus 20.0 meters per second squared, like that. Obviously, 30 squared is 900, 20 squared is 400, so that's 500. So I multiply 500 times 1,000 times 1/2, so that would be 2,500. 0.5 times 1,000 times gives me, excuse me, I said 25,000. It's 2,500, or excuse me, 250,000. So this gives me 2.5 times 10 to the 1, 2, 3, 4, 5. And again, the units work out to be joules. So that is the network required. All right. Now, example 7-9 is pretty useful and it's a conceptual example, but I usually just answer those in terms of words, and I'm going to do the same thing now. It says, example 7-9, conceptual example 7-9, a car traveling 60 kilometers per hour can brake to a stop within a distance of d equals 20 meters. If the car is going twice as fast, i.e., 120 kilometers per hour, what is the stopping distance? Assume the maximum braking force is approximately independent of speed. So this is another application of the work energy theorem. And in this case, I'm actually going to write a little bit with it. Let me go ahead and separate this out by using a purple line. So conceptual. Oh, great. Okay. So what we're using here is V1 is equal to 60 kilometers per hour and implies a stopping distance equal to 20 meters. And V2 is equal to 120 kilometers per hour. And we want to know what distance D2 is. Now, the work energy theorem says that W net is equal to the change in kinetic energy. But in the case of this, the only work being done is the force between the tires and, well, you can sort of think of it, if it was skidding, it'd be the force between the tires and the road, as the friction force on the tire between the tire and the road slowed it down. So that's one way of thinking about it. Another way of thinking about it is that it's actually the force applied, like to the brake pads or the brake disc or whatever, something like that. But the main thing is, in all those cases, the work has the form of some friction force times distance. So this W net equals delta K means some friction force times distance is equal to K final minus K initial, but that friction force, remember, is acting like this way while the car is going this way. And as I warned you, whenever you're doing the work calculations, if your force has a component that's opposite the direction of the actual displacement, then the work should come out negative. So the work net has to be a negative FD, and the fact that K final is zero means that K initial with a negative sign is equal to the negative FD. So with that in mind, we can see that F times D is equal to 1 half mv initial squared, and that tells us that D is directly related to V squared. So that if we double the velocity, we're going to quadruple the distance. If we triple the velocity, we're going to nine-tuple it. If we quadruple the velocity, we're going to 16-tuple it. If we're going to quintuple the velocity, we're going to 25-tuple the distance. So with that in mind, 60 kilometers per hour implies 20 meters, suggests that 120 kilometers per hour suggests not 2 times 20, which would be 40 meters, but 4 times 20, which would be 80 meters. And that's the answer. You could actually work it out, but that's more than enough explanation as well. Now, chapter 8 is called Conservation of Energy. So, chapter 8, Conservation of Energy, is really about some quantity that we figured out over time we've learned that there's certain quantities that seem to be conserved in nature in very neat ways. For instance, one of the first things we learned was conservation of linear momentum, which we haven't learned in this class yet, by the way, but it is a thing that is conserved. Another one is conservation of charge. Another one is conservation of angular momentum. And ultimately, we also figured out that there was some kind of quantity that we have basically termed energy, and it does have units of joules or calories, what we normally use for units of energy. And we found that that has been conserved as well. If we ever found a quantity that didn't energy quantity that wasn't conserved, we would be a little concerned about that, but it would basically take a lot of experiments. And ultimately, what has ever happened whenever we did discover what looked like conservation of energy being challenged, we found that there's yet another source of energy that we hadn't learned about, and that's led us to discover other things. So, for instance, you could figure out studying the nucleus of an atom that there must be some kind of potential energy in there, and if you looked at that without knowing about that potential energy or energy stored up in the nucleus, you would see, oh, wow, it looks like energy is not conserved here. But when you dig a little deeper and see all the forces acting at the atomic level, you'd see that, again, conservation of energy reigns supreme, and it is true. So, what what kind of things lead to these conservation of energy issues? Well, it turns out there's a concept called a conservative force, and other forces are called non-conservative. It's either a yes or no thing. It's a dichotomy. You only have two choices: conservative versus non-conservative, at least as far as what we're thinking right now. Your book says the work done by the force on an object moving from one point to another depends only on the initial and final positions of the object and is independent of the particular path taken. So that is the definition of a conservative force. A conservative force is conservative if the work done by the force on an object moving from one point to another depends only on the initial and final positions of the object as and is independent of the particular path taken. So that's one definition of it. I'll write it here. Conservative force means that if you integrate from point A to point B of F conservative dotted with DL, you're going to get some kind of function phi of B minus phi of A such that the path is irrelevant. So that's one way of saying I'm saying the path is irrelevant, which means you're always going to get the answer phi b minus phi a, which are only functions of the initial position and the final position. And that means if you go from point A to point B, like completely parallel to the x-axis, then completely parallel to the y-axis, that's one path. We could go straight along a straight line from A to B. That's another path. We could go straight along the y-axis and then straight along the x-axis. That's the third path. We could do a hyperbola or a parabola or part of an ellipse or part of a circle from this point to that point or from this point to that point this way. All those different paths always give you the exact same answer if the force is conservative. So that's one way of defining the conservative force. Another idea, completely equivalent, is the force is conservative. The net work done by force on an object moving around a closed path is zero. So this was one way of doing it. Here's another way. Now, what we do when we're doing an integral over a closed path, or a closed surface for that matter, so this is a path integral in this case, but there's also things called surface integrals, in which case you'd integrate over a closed circle, a closed surface. What we do to indicate it's a closed integral or an integral over a closed path or over a closed surface is we write a circle on the integral symbol. That's all it is. It's not any different technique of calculus. You just put the circle on there, and it's a good little reminder that, hey, this is applied to a closed path or a closed surface. There's actually going to be a law that we'll learn later that involves an integral over a closed surface and another one that involves an integral over a closed path. And in those cases, it turns out that they're not necessarily zero, and there's a very good reason for it. But the specific thing to understand is those equations wouldn't necessarily be true unless you were doing that integration over a closed path in the one case and a closed surface in the other. So that's why we need them to put them there. It's not just for convenience or reminder, it's also to tell us when the law is actually valid. So in this case, what we're talking about is F conservative dotted with DL over a closed path is equal to zero. So that's another definition of it. And in fact, there's a bigger, deeper thing at work here. It turns out there's this theorem that you'd learn in a more advanced class that basically says, hey, if one of these facts are true, then all of these facts are true. Let me quickly tell you what those facts are. One is the integral from a to b of f dot dl is some function of b minus some function of a and is independent of the path. That's one. Another one is f is a conservative force. Another one is the integral over a closed path of f dot dl is equal to zero. That's the third one. So again, if any one of these are true, all are true. So if someone told you, hey, a force is conservative, right now you know, oh, okay, that means the force, the integral of the force from point some point A to some point B is equal to a function of B minus a function of A and doesn't depend on the path at all. That's one of the conclusions you can reach when someone tells you a force is conservative. Another conclusion you can reach when someone tells you a force is conservative is that the integral over a closed path is zero. Another thing that you can conclude is, I already said it, but I just want to put it here, F is a conservative force. Notice how I slipped from it being a definition in case one and a definition in case two. Now I'm treating it as if they're just separate little ideas. And we've added a new idea to it that F is a conservative force. And again, this theorem states that if any one of these are true, all of them are true. Here's the fourth one. Del cross F is zero. And the triple equal sign that I'm saying here implies, oops, that was supposed to be implies, and I put implied with a D, implies that uh, del cross F is exactly zero in all cases, not just at certain positions. So in other words, if del cross F is, we call it identically zero, that means when you do this weird determinant thing that I haven't taught you yet, if the answer doesn't come out to exactly zero, it's got like X's and Y's and Z's and T's and stuff like that in it. If that's really the case, then it should come out to be just zero, independent of what X, Y, Z, T, or W, or whatever these other variables are. It's not that it's zero when you choose a specific set of variables, it's that it's always identically zero. So that's another one. And in fact, there's another one that has to do with basically, uh, I will, you're not really ready for this one that much. Neither were you with the cross product, by the way. So I'm not going to put exactly precise wording on this, but basically, uh, you can say that df is equal to the partial of f with respect to x dx plus the partial of f with respect to y dy plus the partial of f with respect to z dz. That is called a differential, and it makes for an exact differential equation. And if you happen to have a conservative force, that can generate a exact differential equation, and that's kind of important. And the other thing is that, and here I'll use some mathematical symbols. The upside down backwards e is there exists a scalar function u such that, and that's the symbol, mathematical symbol we use for such that f equals the negative gradient of u. Okay. Now I've used this triangle now twice. I used it in the part four, and now I've used it in six. So I'll tell you what this is. This del is an operator. We call it del or nabla or a gradient, and it's a operator. You can put it next to a vector, and it acts on a vector in a very specific way, or you can put it next to a scalar, and it makes a vector out of it. So I'll leave it as if it's a upside down triangle with a little space here. So I'm just putting that underline there to mention that, hey, something's supposed to go next to this. And what you end up doing to writing it, at least in Cartesian coordinates, is you write I hat times the partial with respect to x. Notice we're leaving a space just like we left a space next to the triangle. Then we have j hat partial with respect to y, again leaving a space, plus we have k hat partial with respect to z. That's what the gradient is. And in Calc 3, you'll learn about it, but basically the gradient, if you take the gradient of a function, that in some sense gives you something related to the slopes, and it also tells you sort of the path of least time in some sense. So that's one way of using it. We could also use it as del cross F. In that case, what we do is we take a determinant of a matrix. So I'm going to write it this way. I'll say determinant of a matrix. And the matrix has the first row as I hat, j hat, k hat. The second row has the vector f, so I put the x component right, or excuse me, no. The second uh, row has the components of the gradient, which is partial with respect to x, partial with respect to y, partial with respect to z, and then the third row is f sub x, f sub y, and f sub z. And from that, you get a very specific operation on the function f. And you could work that out. We'll do it later when I show you actually how to do this cross product, but I just wanted to let you know what it is. There's also another one where you could do del dot f, and that would be uh, the partial of f sub x with respect to x plus the partial of f sub y with respect to y plus the partial of f sub z with respect to z. And notice that is a scalar. That's because it's a dot product. This one, as I said, is called the gradient. This one's called the divergence, and it's a scalar. And this one is called the curl, and that's a vector. So if you let the gradient operate on a function, then it spits out a vector. However, if you let the gradient act through a dot product on a vector, it spits out a scalar. But if you let the gradient act on a vector via the cross product, then it spits out a vector. So that's it. But this is the deep underpinnings of all this. Evidently, when you find that such a conservative force exists, in other words, someone tells you there's a conservative force, then you get all these other things that you know about it, and they are related to your differential equations class when you study exact differential equations. Those are the ones where you have like some function times dx plus some other function times dy is equal to zero. And what you do is you take the function that's in front of the dx, you take the derivative of that with respect to y, and you take the function that's in front of the dy, and you take the derivative of that with respect to x. And if those two derivatives are equal, then you know it's exact because what you've now done by it being multiplied by dx, you're going on the assumption that that function that was already there was the partial derivative of f with respect to x. And by taking the derivative with respect to y, you've now done the partial derivative with respect to x followed by the partial derivative with respect to y. And the same thing on the other one. It was the function and multiplied by dy, and therefore you assume that function was the partial derivative of f with respect to y, and then you took the derivative with respect to x. So you had the second derivative of f with respect to x and then with respect to y. And in calculus, under most conditions, the order of the derivative doesn't matter. So the partial with f with respect to x followed by the partial of that with respect to y is the same thing as when you do it in the opposite order. And because of that, you end up getting basically that the function is ultimately a differentiable function. It's exact differential, and the integration is just, or the solution to the differential equation is just found by integrating one of those functions with respect to a variable and adding a constant with regards to the other variable. So that's where all that's leading to. Again, I'm trying to talk as lowbrow slash highbrow as I can. Like I want to get the information to you, which is somewhat highbrow, but I also want to talk where it's somewhat lowbrow so that you'd understand without being too tripped up by all the intricacies of mathematics you haven't been taught yet. So, with that in mind, what we now are given is a way to actually compute the potential energy function, and that's the main one of the main points of this course, and specifically chapter 7 and chapter 8. That's the main points of those two chapters. Is if you find that a force is conservative, you can generate a potential energy function as a stand-in for that, and that allows you to do physics without vectors. You actually can do physics as if it's all scalar, and that makes it a lot easier. There are things that still require you to go back to the vectors to study to make sure you can do the scalar versions of the equations, but generally it's still a lot easier. And you can still get all the variables back, but you might have to use some vector considerations as well. But here's the technique. The technique to determine the potential energy of any kind of conservative force is you calculate the work done by the conservative force in moving from point A to point B, for instance. So you calculate the work done by this conservative force in going from point A to point B. And then you say, okay, that's the force done by the conservative force, and that should give you some function minus some other function. And it's not necessarily even a function, but I'm going to pretend like it is, just because I haven't thought about whether it is. I think it is. But some function minus another function is what you're going to get for that conservative force when you calculate the work done by that conservative force and going from A to B. And what we're going to tell you is that the potential energy is defined such that the change in potential energy is equal to the negative of that work done. So the potential energy, the potential energy change, oops, in going from point, I don't know why I put that extra little herky jerky up there, from point A to point B is equal to the negative of the work done by the conservative force and going from A to B. So what we're saying is change in U is equal to U final minus U initial. I should put this as delta U just so you'll know. That's equal to the negative of the integral from A to B of F conservative dot dl. So not only is that telling you what the potential energy function is, that's actually the prescription to calculate a potential energy. So for instance, if we want to calculate the potential energy of the Earth's gravitational force near the surface of the Earth, then we can recognize that the gravitational force is just the mg pointing down. So let me show you exactly how we go about computing that potential energy function now that we have this as a plan. So what we do is we can imagine in an XY coordinate system, we can imagine a mass M that is subjected to a force W equals mg. And technically, if you want to make that a vector, you'd say mg negative. Let's go ahead and do that. I'll go ahead and make it a whole vector so it'll be a little bit easier to jump right into. So that's negative mg j hat. And that is the actual conservative force as well. Okay, I'm going on the assumption I haven't told you that yet, but gravity is one of the conservative forces. The electric force is another one that's conservative. So that's two that you need right now. But that's our actual conservative force. And what I want to do is imagine moving this mass m from x equals 0, or excuse me, from 0, 0 to 0, y. So I can put this up here, and of course I'd call this point A, and I'd call this point B, and it's up a distance y. So if I calculate the work done by the conservative force in moving the object from A to B, then that calculation goes like this. W is equal to the integral of F conservative dot dl. Now I'm doing this in a straight line. I could technically go from 0, 0 to 18y, 18 comma y or something like that. Wouldn't matter at all. But I'm doing it the simplest way right now. So the work done in it moving from A to B is equal to the integral of negative mg j hat dotted with, now I'm going in the positive coordinate direction, so that's going to be dy j hat, and I'm going from y equals 0 to just plain y, and obviously we get a negative mg, which is a constant that comes out in front, and I get dy j hat dot j hat, which I think you all know since we've done I hat dot I hat so many times, that j hat dot j hat is also 1, and I end up getting negative mg, and again this is from 0 to y. I get negative mgy. So delta u, therefore delta u equals negative of the work done by the conservative force, means that delta U, which is U final minus U initial, is equal to negative of negative mgy. So what we find is U final is equal to mgy plus U initial. And believe it or not, we're actually allowed to choose the zero of potential energy to be anywhere we want. So I'm going to choose UI equals 0. Okay. So what you do is you set in this case, the variable that came out was y. So you say, I'm going to call y equals zero, the zero potential energy. If that was on top of a building, some other person might look at that and say, hey, that height is not zero. That height is 10 stories up. So they would call maybe the ground level y equals zero to have zero potential energy. But at the end of the day, in you moving it from the roof to 10 meters above the roof, are you moving it from 10 stories up to 10 stories plus, 10 meters above? You still get the same change in potential energy. And that's really what matters. Ultimately, it's the change in potential energy that matters, not the absolute value of the potential energy. Sometimes there's a natural way to define the zero potential energy. Like, for instance, when we're talking about the gravitational force, it's natural for us to consider infinitely far away from the source of the gravitational force should be the point at which we reach zero potential energy. And when we do that, we get a potential energy function. So now what we've discovered by this process is that the potential energy U of y for gravity is actually equal to mgy, and y equals zero is up to you. You get to choose what y equals zero is. Or excuse me, you get to choose what potential energy equals zero is, and that corresponds to y equals zero. Okay? So you are free to choose what y equals zero corresponds to. In other words, wherever you put your coordinate origin, you're probably going to say, okay, well, at the coordinate origin, that's obviously y equals zero. So if you put that at the top of the building, you're calling the top of the building potential energy equal to zero. If you're the person down at the bottom of the building looking up at this person doing this, you might call y equals zero the ground level, in which case the potential energy at the roof is 10 stories times mg. In other words, 10 stories converted to meters times mg. And then when you move it up, it's that not only the height that you had from the roof to the top, it's the roof to the top plus the height to the ground. So that's how that works. We can do another one, for instance, if we wanted to consider the gravitational force in pulling an object out. So let's imagine, for instance, there's a big mass M here. This could be like a planet or something like that. And the radius of this, by the way, is just plain R. Or let's do, well, actually, we don't even need that. We just need a distance away from it. So what we're going to do is imagine this is our x-axis, this is our y-axis, and this is our z-axis. And we're going to imagine bringing a mass in from a very long distance away. So point A is at R approaching infinity, and we're going to bring it into point B at R, and that's R is the distance from the origin. That's the or that's the spherical coordinates that we're talking about here. So it's just literally the distance from the center of the object to here. That distance is R. Now, if you actually have a body that's causing the gravitational force and you're wanting to know the potential energy inside of it, there's some more work that has to be done. I'm not showing you any of that. This is when we're trying to calculate the potential energy outside of the body. So now I'm going to calculate the work done by gravity, or which is the conservative force. So work done by the conservative force is equal to, again, we're going to calculate that and then use the negative of it to make the potential energy. So I'm going to do the integral of the force of gravity would be G big M. Again, remember I'm saying the big M is the mass of the thing that's causing the gravitational field. So it's that, and then I'm saying the mass that we're moving is a mass little m, and then of course it's inversely proportional to the square of the distance between them, and this force should actually point in the negative r hat direction. In terms of what r hat is if you imagine a point A in space, and then you draw a line from that point A in space all the way back to the origin. If you drew an arrow pointing this way, that would be the negative r hat direction. If you drew the arrow pointing this way, that would be the positive r hat direction. So you see, gravity does pull it in the negative r hat direction. So that's why I called it negative gm r hat. But now I've got to also take the dot product of that force with my dl vector. So I move the integral over so I can put these in quotation, I mean in parentheses. And now the integration that I'm performing is going in the negative coordinate direction. So I'm going to call this negative dr r hat. So I'm letting the actual DL dictate which to, or tell the, I'm letting the DL inform us as to the direction of integration. Since I've done that, now I've got to choose a positive coordinate direction for the limits of integration, for the range of integration. So I'm going to integrate, in fact, from a small number to a large number. So I'm going to integrate from R to infinity. Now the two negatives cancel each other out, and I can pull a mess load of stuff out in front. I'm going to get positive g m m like that times the integral of r to the negative 2 dr r hat dot r hat, which is clearly 1. And now I get the integral of r to the negative 2 is negative 1 times r to the negative 1. So I end up getting negative g m m r, and this will be evaluated from r to infinity, which equals the limit as r approaches infinity of, and I'm going to keep this negative out in front right here, of, actually, if I'm going to keep that negative, I need to put it in parentheses or bracket or something, so I'll do it right here. I'm going to say equals negative. Now I get G M M. Oh, this is the part where I need to limit, and I forgot to write limit again. Stupid head. Oops, that's not good. Okay, so I'm taking the limit. That's how you deal with limits of integration that are infinite. So I'm taking the limit as r approaches infinity of G M M over r minus the value at r. So that's going to be G M M r like that. That limit gives us 0. And in fact, we end up getting 0 minus r is negative. I think that, ooh, that negative was not supposed to be there. Oh, yeah, yeah, it was. It was supposed to be there because of that, because the integral of r to the negative 2 is r to the negative 1 divided by negative 1. So that's where that negative came from. And this gives us, in fact, G M M over R with a negative in front of, or actually this with a positive in front of it. So that's the work done by the conservative force, and therefore the potential energy U has to be the negative of that. And that is U zero, U final minus U initial. And U initial was technically at R equals infinity. We're going to call that 0. So we finally have from all this delta U, which equals U final minus U initial, and U final is at R distance away, and U initial is at R at infinity, which we're going to assume to be equal to 0. Now, all of that is equal to the negative of the work done by the conservative force, and we just computed that was G M M over R. So what we now know is U of R is negative GMM over R. So now I've got two potential energy functions. If you're near the surface of the Earth, the potential energy is just mgy. If you're out some distance that's comparable to the radius of the Earth, from the surface of the Earth, then you have to use this other form, U of R equals negative GMM over R. Now, normally conservation of energy, and your book does this too, it does it two different ways, but one way of doing it is this. You say delta U plus delta K. Those are the only two mechanical types of energy we've learned so far. And we say the sum of those two is equal to zero. Alternatively, since delta U means U final minus U initial, and delta K equals K final minus K initial. Because of that, you can also say, I'll write it somewhere else because that's not big enough. Or you can say U initial plus K initial is equal to U final plus K final. Those are two ways to implement conservation of energy, but they're not the ways that I choose to do. What I choose to do is your instructor's technique is I do U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. And technically, I could have put another E term on the left hand side, but I haven't found a need for it because all of these terms are terms that can be that can have separate terms. So, for instance, kinetic energy can have a term that's just kinetic energy for velocity in the x direction, in which case it'd be 1/2 mvx squared. Then another one, 1/2 mvy squared for the velocity in the y direction. Then another one, 1/2 mvz squared for it in a third direction. Not only that, you also have another kinetic energy associated with rotating about an axis, and that could be 1/2 I omega squared. So each of these terms can have many terms associated with them. Same thing with potential energy. That could be potential energy due to gravity. That could be potential energy due to electric field. It could be potential energy due to a nuclear force, all that sort of stuff. But in here, I'm using work in to allow for those non-conservative forces, like if a father gives his child a push on a sled before they slide down a mountain, you could calculate the work done by the father in pushing the child and then use that to calculate how fast the child was going at when they reached the bottom of the hill. That work in would just be the calculation of the work done by the father. The work out might be, for instance, if you used a bumper system with a spring-loaded bumper at the bottom to slow the child down, you could, instead of calculating how fast the child would be going at the end, you could calculate how far the child would compress the spring-loaded bumper in coming to a stop. And in that case, work out would be 1/2 kx squared, where x is the amount of compression you did on the spring. You could also take into account, for instance, the loss of energy due to friction, and that's what I call E loss. Again, you could also call 1/2 kx squared E loss. That would be fine either way. The main thing is you only want to count each source or diminution of energy. You want to count each of those once and only once. Okay, so you could take into account the loss of energy due to the work done by friction, in which case you just put F times the distance traveled or whatever. Notice I do not use, when you're doing this, U initial plus K initial plus work in plus equals U final plus K final plus work out plus E loss. I don't use any negatives. Okay. The only negative we ever use when I'm using this technique is this negative sign right here. Everything else should come out to be positive. So instead of E loss, which would give you a work calculation that give you a negative quantity, you just take off the negative symbol and the negative sign and put it in there anyways. Okay, I'll work examples next time, but this is enough to get you started on doing chapter 8 and understanding it. And I will call it a day. Thanks for watching my video, and see you next time. Bye bye.